by a linear scan. It's more like, things are fermenting here, some things are happening here, you're swapping them around. Overall it's order n, but the constant factor is, let's look at build heap. Let's look at the build heap operation so that um, so here's the question overall. How do you build a heap? How do you build a heap with 10 elements? Well, one simple way to build a heap with n elements is to insert each of those elements one by one into the heap, and that we've seen is going to be order n log n, right? Because the way I described heap sort, what you're doing is you're building this heap by inserting the n elements one by one, and then you're executing the remove max operations one by one to get the elements in reverse sorted order, which you can easily change into a sorted order. Um, but actually we can do better than this, and the algorithm itself is uh, let me actually take an example. But to understand this build heap procedure, we'll need to also understand a procedure called Heapify. The book actually uses uh, heapification. It talks about heapification, and then it uses heapification in the process for building a heap. So let's first look at this operation called Heapify, which will be used in the build heap procedure. Okay. So what is Heapify? So let's take a node. Now this node is going to have a left subtree and a right subtree in general. And this node could itself, this is an internal node in the tree, doesn't have to be the root. So let's take this node in your heap. Now assume, by the way, this is something that should be obvious, but if it's not, let me state it clearly. If you take a heap and if you focus on any subtree in that heap, that itself is a heap. Okay, so when you take any heap, let's say this is the root of the heap, and this is the left subtree and the right subtree. If this whole thing is a heap, if it satisfies the shape property and the heap property, then the same is true for this subtree as well as this subtree. Because if any of them violate the shape property, the overall heap cannot have the shape property. And if any of them violate the heap property, then the whole thing cannot satisfy the heap property. That should be clear enough, right? So we are going to assume that the left subtree, the tree is rooted. I'm going to call this node as I. So this is I in terms of the index of the array. So note that we're still looking at an implementation in an array. So we're looking at the ith element here in this heap. And what we are saying is that the left subtree, or the left subtree rooted at the left child of I, and the right subtree rooted at the right child of I, both of them are going to be max heaps. Right? If the whole thing is a max heap, these two are also going to be max heaps. This should be fairly straightforward, but if you have any questions, ask. I mean, I wanted to write this down, but I think it's clear enough. So any doubts about this? Now what we're going to do is we're going to assume that there is a problem in the satisfaction of the heap property here at this node. So what Heapify does is It's a general procedure that applies when a single node has a problem with the heap property. Now, what sort of problem can there be? Well, the heap property says that the value at this node should be greater than equal to the value at both of these two. Now, suppose that's not true, but we are assuming that that's not true only at this node. So in the rest of the tree, there's no problem. Just like in the insertion operation and in the remove max operation, we saw that when we try to maintain the shape property, we end up violating the heap property, but that violation is local. It's local at one particular place. So likewise, now we want to look at a generic procedure for correcting the heap to satisfy the heap property when something goes wrong at one place in general. It could be anywhere. It could go wrong at the root. It could go wrong at a leaf. But actually, things go wrong between a node and one of its two children. So how do you correct such a scenario? We've already done this in some sense, but I'm asking a slightly more generic question here. So how can I correct? So let's say that one of these two children, or both these children don't satisfy the heap property. So their value is actually greater than the value at this node. What should one do to correct this situation? So okay, this is A of I, and I'm going to call this as A of IL, the left child of I, and A of IR, the right child of I. So we can compare AI with both of these. Hmm. Yeah. Yeah, so I'm asking about the implementation of Heapify on AI. So how do we implement, so heapification is a procedure by which we correct the tree to make it satisfy the heap property when something goes wrong at one particular node. And it goes wrong in this particular way. So it violates the heap property. So what was proposed is actually correct. We look at which of these two is the larger value, and then we swap A sub I with that larger value. Now that will potentially shift the problem down one level. Okay, let's say this was the larger value and this was swapped with A sub I. Now, because we have swapped this with a smaller value, note that this was a heap before, right? So this was the largest element. Hmm. Yeah. It's going to be log n. In fact, it's going to be log of whatever the number of elements in this subtree, because this node could be anywhere in the heap. So because we'll be syncing this node down following that procedure, the same procedure that we use for extract max. I mean, think of extract, if you go back to extract max, or remove max, we were basically doing heapification at the root, right? Because things went wrong at the root when we swapped the last element with the root, right? In order to extract the maximum element, we removed this element and we replaced it with the last element to maintain the shape property. And then we noticed that the heap property got violated here. So we basically bubbled this node down to make it reach its appropriate location by swapping it with whichever of its two children was the larger one. So effectively, that's what we are doing here. But we are saying that things can go wrong not just at the root, they could go wrong anywhere. And we'll see how this kind of a scenario arises when we look at build heap. So that's what we do here also. We bubble this node down. I mean, if you just imagine that the heap had just been this, then this is clearly the root of that subtree. So We'll move this down, we'll move this up. And because this was already, yeah, so the complexity of this is going to be order of log of n, where n is, you can say, the number of elements in this subtree. So any questions about heapification? So this is what in essence it is. If a sub I is smaller than its children, heapify of I